Hello and welcome back to Electronics with Emrys. In this video I'm going to be showing you how to use a simulator to design a simple common-emitter amplifier. Before we do anything else, we're going to need a simulation model for our transistor. I'm using the MPS 8098 NPN transistor because it's what I had on hand. After doing a quick Google search for the SPICE model of this device, I found a forum where someone had posted a good model for it. One of the things I really like about QSpice is you can copy a SPICE model like this directly into your schematic. Just clicking inside the schematic area and pressing Ctrl V brings up this dialog. I can choose yes to auto-generate the symbol, and now I have an MPS 8098 transistor that I can simulate with. Looking at the datasheet from Central Semiconductor, in my application I'm looking to use a 15 volt power supply, so the breakdown voltage of 60 volts here is going to work out just fine for me. Looking at the current gain, or the HFE of this device, we see that at 5 volts 1 milliamp IC, that's between 100 and 300. So this is also called beta if you're used to seeing it as that. It remains at least 100 with 10 milliamps of collector current, and then starts to dip down whenever you get to 100 milliamps. I'm planning to use it between 1 and 10 milliamps, so this should work out perfectly for me. One other item to look at is the gain bandwidth, and here we can see that this works at least at 150 megahertz, which is well beyond the audio range that I'm going to be designing for. Now that we know the basics of this transistor, let's talk about the circuit and what all I need to know before I get started designing. The first thing I need to know is, what is my load? What am I going to be connecting this amplifier to? And in my case, I'm connecting it up to an analog to digital converter card on my computer. And that has an 11 kilo ohm input. So I'm going to represent that with an 11 kilo ohm resistor over to the side. Whenever I do connect this, I'm going to use a decoupling capacitor to isolate my bias on the left side from the input to the ADC on the right. And we're going to rename this to RL. I'm going to add in the 4 common resistors for a common-emitter amplifier, with R1 and R2 being these standard resistors for the voltage divider biasing. And R3 and R4 are going to be renamed to RC and RE. My supply is going to be 15 volts. And if you need to select multiple items in QSpice, you can hold Shift and drag to select an area. Then whenever you let go, that will be connected to your cursor, and you can click it back where you want it to be. I'm using a lot of keyboard shortcuts here. W is for wiring, C is for capacitors, R is for resistors. Most of them are very intuitive. So the majority of the work for setting up this transistor the way we want it is going to be in choosing these resistor values. Really, when I say designing an amplifier, I really mean choosing these resistor values to make the amplifier do what we want. So what exactly are we trying to do here? Well, we know our load resistor, we know our supply, we know which transistor we're using. So this is the majority of what you need to know. I could immediately choose RC to be 11K, which would impedance match my amplifier to my load. And that would mean that I would be getting maximum power transfer from the output of my device to the load. But in my case, I don't actually want to be getting a maximum power transfer. This isn't a case where I want to be amplifying power. I want to be amplifying signal. This is acting as a secondary stage for a preamplifier of a microphone. So I'm going to be taking relatively small voltages and amplifying them up to large values of voltage, not of power, just so that they can be read into the ADC on my computer. So instead of using 11K, which would match power, and I would lose half of my voltage in this voltage divider, I'm instead going to change to a 1 kilo ohm resistor here, where I'm going to get a voltage divider again, but the majority of the voltage, 11/12 of the voltage, is going to end up at the load instead of across my collector resistor. So before I solidify this choice of a 1K resistor, something I want to do is to verify that the amount of power across this resistor is going to be acceptable. I'm planning to bias the output of this to about half of VCC. So we're looking at about 7.5 volts at the output and 7.5 volts across this resistor. So if we have 7.5 volts across a 1K resistor, we're able to easily calculate the power. The power across a resistor, when you know voltage, is just the voltage squared divided by the resistance. And that's 56.2 milliwatts, which is well within the range of an 1/8 watt resistor. Now, if we wanted to go with the worst possible case, which would be with all 15 volts falling across that resistor, we'd be looking at 225 milliwatts, which is a little more than my resistor can handle. But I don't expect all the power to fall across this resistor. We're going to have some on the transistor, and we're going to have some on RE also. So we should be fine with a 1K resistor here. The next question is, what value should RE be? And there are two things that we need to consider whenever we're looking at the value of RE. Number one is the gain of the circuit, because the gain of the amplifier is going to be the RC value divided by the RE value, or at least it'll be very close to that. So if we set RE to be 100 ohms, we know our gain is going to be 10. 1K divided by 100 gives you 10. There is an issue with DC bias here though, as the voltage at the top of this RE is going to be larger than 0, which means that we are reducing the range that our output voltage can be, because without this resistor, our voltage can go from 15 volts down to almost 0. Our transistor is going to have a little bit of voltage at the bottom end here, maybe 100 to 300 millivolts. But if we have 100 ohms here, now we have a significant portion of our voltage that's going to drop down here, but not that much. In this case, it's going to be about 1/10. I chose this to be 1/10 the size, specifically so that I would be getting about 1/10 of the voltage here. So we're saying maybe a volt across that resistor, and that really shouldn't give us any problems with range. I'm expecting my output voltage to be between 1 and 3 volts peak to peak, so we really shouldn't have any problems with a 15 volt supply having not enough range for that. If you have a smaller voltage supply, then this resistor could affect that. Now, the other thing that this resistor does, and one of the big benefits of this resistor, is that it makes your biasing circuit much more linear whenever it comes to setting your bias point. So if you don't have a resistor here at all, you can imagine this. If this were 0 ohms, or we just took it out and shorted to ground, then VBE would be connected directly to this node. And VBE is a diode. So whenever we increase our voltage on the left, it would increase from 0 to about 0.7 volts with no problems. But then it would clamp there. The diode would hold you at that voltage. And you could change these resistor values a great deal and have almost no change in this voltage. And that would mean that you'd have a hard time getting exactly what bias you want. Adding some resistance in here kind of gives a cushion so that there's some voltage across RE, and then your values of R1 and R2 can be less precise and still give you the correct range and operating point that you're looking for. Now, maybe the hardest part of this circuit is determining R1 and R2 to be the numbers that we want. One of the general rules of thumb for designing with this circuit is to do 10 times the base current through R2. What I'm going to do is place in a voltage source over here, and this is going to represent a resistance. So I'm going to put a piecewise linear function here. At time 0, it's going to be 1 milliohm. And at time 100, it's going to be 100 kiloohms. So that means we can use the time scale of our output to fairly accurately determine what the resistance is. Every second is going to be 1 kiloohm. I'm using a very large time scale here also to make sure that there's settling time, and this will be basically a DC measurement. You wouldn't want to do this in 100 microseconds because the capacitances in the MPS 8098 would throw things off for you. Just labeling this as resistor or resistance, I'm going to replace R1 and R2 with variable resistors. And in QSpice, if you press B, you'll get an expression-controlled voltage source. Press it again, you get a current source, and a third time you get a resistor. For the bottom resistor, we're just going to say the voltage at RES, so that node right over here relative to ground, And that's just the resistance value that we're outputting in that PWL function. And then for the other resistor, we're just going to do 100K minus the voltage at RES. And then we're going to put in a transient function for 100 seconds and run our simulation. I'm looking for a very specific operating point. I want my output to be about halfway between VCC and this bottom point. So now remember I said adding in RE means that we're not going to be able to go all the way to ground, and you can see that here in our output curve. We're only able to go down to about 1.5 volts. So what I'm going to do is say, well, let's go to around 8 volts as our halfway point. Just to set this to 8. And then that's happening at 11.7 seconds, or 11.709 kiloohms. So I'm just going to replace this whole function here with 11.709K, rerun it to double check that I have exactly what I want. You can mouse over a particular component to see the current through it. That's 7 milliamps. And mouse over this, I have 7.9 volts. That works for me. So now this first stage is just to get an idea of what we need. So this is giving me the resistance for basically R2. I'm going to go ahead and replace this guy. Keep it named R2 to be consistent. And this is going to be a 10 kilo ohm resistor. Because I don't have an 11.7K resistor, the closest I've got is a 10K or a 15K. So I'm just going to put a 10K. Now I'm going to go back to my PWL function, and I'm going to say B1 is now going to just be VRes. So now I have a 10K set resistor, and I've got a resistance at the top for R1 that's going to be some number between 0 and 100K. We'll rerun this again. Look at our output voltage. And now when I go to 8 volts, I see that that's 78.807K. So we're going to get rid of that. 78.807K. Go ahead and get rid of this because I don't need it anymore. And I'm going to rerun and double check my bias. So here I've got about 7 milliamps and about 8 volts. Perfect. That's exactly where I want to be. Doesn't have to be absolutely precise. You just want to be very close to that midpoint so that you have lots of room to play with on the going up and down. Remember, this is an amplifier, so the whole point is your output is going to be varying up and down depending on how your input varies. So you want to have as much room above and below this midpoint voltage as possible for your signal to travel. Also, your signal being in the middle means that you're going to have better linearity from the input to the output. So now that I have my circuit set up, I have configured everything the way it's supposed to be. I'm going to go ahead and add in my input voltage. And this is going to be set up for an AC analysis. So I'm going to say AC equals 1. You have to give it a value of 1. This is a common thing in simulators, and if you're used to Spice, it's something you just kind of pick up along the way, but AC equals 1 is required to do an AC analysis, and if you don't have 1, then you won't get the correct gain numbers at the other end of your circuit whenever you test. So now I'm replacing my transient simulation with an AC analysis. I'm going to do a decade analysis with 101 points per decade from 1 hertz to 1 gigahertz. And then we can run this, and then we can observe the output voltage on our RL here. And that'll tell us the gain. I'll click this one more time there we go. My gain here is 18.8 dB, which is very close to my expected 20 dB. 20 dB is exactly 10 times gain, so I'm getting a little bit less than 10 times gain. Let's change my load out, because this is, whenever you look at the gain of this, it's assuming there's no load. So I'm going to change this to a 1 mega ohm load instead of my 11K load. And we can see here that our gain is 19.6, much closer to 20. So very close to what we were expecting. If that's not enough gain for you, there's a couple things you can do. But the simplest thing to do is to just take a capacitor and put it in parallel with this resistor. And this is called a bypass capacitor. And specifically because it allows AC signals to bypass this resistor, and you are able to increase your gain only for the AC signals by a significant amount, while your DC bias is completely unaffected. So we're going to run this one more time. Now here you can see my gain is much, much higher than what it was before. So we're looking at 48 dB of gain here. But I'm getting a cutoff frequency that's much higher than what it was before, because my cutoff was way off to the left over here down in the low hertz. But now we're looking at around 100 hertz. Let's see. We're going down to 44 at, what is that, about 300 hertz. So that's much higher than what I want to see. So the easiest way to fix that is to just increase the capacitance and rerun our simulation. We'll see that the frequency has moved to the left much further. So now we're looking at around 40 hertz, which I can live with. I don't mind losing a little bit of the bottom end of my microphone, but that gives me a great deal of gain for a second stage of my preamplifier. So realistically, we're done. This is a completely functional amplifier design. You can run it with or without this capacitor to be able to get the gain you want. But hopefully you got something out of this. If you have any questions or comments, please leave them down below in the comments section. And thanks for watching. Have a great day.